Okay, so as always, if you got a question, let me know. But what we're going to talk about today in our little bit of class here is a continuation of forces from yesterday. Now, yesterday when we talked about forces, we did a lot of like, here are the fundamental forces. Here are the strong nuclear forces binding the nucleus together, electromagnetism with positive and negative charges, weak nuclear forces causing radioactive decays, and gravity, which is causing things to fall and for me to fall down the steps over and over and over again. What in the end we saw is that all of the forces can be thought of as the same, or we at least think they should all be thought of as the same. And when we do that, we really think of forces as just a push or a pull on something. Okay, they're just pushes, they're just pulls. That's all we're talking about when we talk about forces. What we're going to do a little bit today is we're going to take it over to the lab, and we're going to take a look at one of these motion carts, which I've got, and we're going to do a little bit of a lab demo kind of setup with it and see how, if we pull an object, it could start speeding up or accelerating, and what are some of the things that could change the acceleration of this object. And hopefully by doing that, we'll be able to see just how forces influence things and what are some of the variables or features that actually influence forces acting on objects. So let's get into the lab. And for the lab, you'll see that we've got two kind of screens here. One is right here, hi, and then one will be in the back of the room like this. You'll see over here. And we also have got the computer screen, which is kind of like right here. And what I'm going to do here in the lab is I'm going to take the encoder cart, I'm going to put it off to one edge here. And if we come back to the computer, I'm going to zero out this computer cart. So I'm going to come down to its position and I'm going to click 0 here. So now the cart thinks that this right-hand side right here, that right-hand side where the cart is the 0 position. And as the cart moves this way, it's moving like 10 centimeters, 20 centimeters, 30 centimeters, and then this is 0. Okay, so this is our 0 position. Now, what I'm also going to do is I've got here a little bit of a red pulley string. Okay, so it's just a red string. I've got enough of this to last me all the way through retirement. And I'm just going to hook one end of it onto the cart, and then I'm going to run the rest of the pulley string down the track. And as you can imagine, it's going to go over a pulley, which is at the end right here. Okay, see that on the second screen? Now what I also have here, and this is really small, this is just a small 20-gram mass. It's like if you put 20 pennies in your hand or like 20 paper clips, it's next to nothing, okay? You've taken multivitamins that are bigger than this thing, okay? So it's just a tiny, tiny mass. But what we can do with it is I can put it at the other end of the pulley rope, and this mass will fall down because of gravity. There's a weight there, and it's going to pull the cart to the right. What we can do is we can see how the cart's position is going to change in the top part of the graph and how its velocity is going to change in the bottom part of the graph. And by doing so, we've already taken a look at position and velocity graphs. We'll have a good idea of what's going on with the cart. So let's start the recording and collecting data, and then let's just put this mass right on. So here we go. And what do we see? So when we look at this, the nice curve on the position graph shows that our object is speeding up, and it's speeding up. When it gets up here, this is where we're stopping the object, and that's why the mass has hit the ground, so we've reached a peak velocity. We're not pulling it anymore, there's no more force acting on it, but our velocity increases here. And we know that this slope of the velocity graph is the acceleration. So if we wanted to, we could take this here, and we could apply a curve fit, and we could find the slope of that. It's like 0.28, okay? Now, let's run this same thing again, but let's this time change things up a little bit, okay? So what we're going to do this time is we're still going to use the small 20-gram mass to pull the cart, but this time I can put in the cart these little masses here. They're just small, like metal masses. Each one's maybe like 200 grams or so. I'm going to toss 3 of them in the cart, just side by side like that. And then I'm actually going to take another 500 grams. Okay, this is like a fistful of quarters. And I'm going to take this and put it in the cart as well. So the cart is much more massive at this point in time. Okay. So let's collect this and see just what happens with our graphs now whenever we start collecting things. So we start our collection, we run over here, we put the mass on, and then bam, it hit the floor. So if we compare the data sets, notice how in this second data set, that velocity is a much lower slope, right? In that first data set, we're like super steep, and now we're like really shallow. And in the first data set, we increased our position very quickly, but now we're kind of like shallowly, that's not a word, shallowly increasing our position, okay? So we're not speeding up as fast. We're still speeding up, but our acceleration isn't nearly as much as it once was. And that kind of makes sense. Like if you've got a more massive object, it's harder to push. If any of you play football, you know, a really, really big lineman is harder to push than a 3-year-old. I can easily push a 3-year-old over. Don't push 3-year-olds over, but you could if you wanted to. But that's what we're seeing in this slope here, okay? And if we really wanted to, and let's have some fun here. Let's do this. If we take all the masses off real quick. So we've got this very little mass system. We can full send it. And I always tell my students, don't do this. It's dangerous. You'll hurt the equipment. But it's my equipment, so we can do what we want. So what we're going to do is we're going to use this giant 500 gram mass here and just yank, like boom, right onto the system. So let's start the collection, and then... I love that. So... you see when we do that last one, that in comparison to the other data sets, we quickly move across, and the slope here is much greater. And if we actually do go ahead and look at the acceleration graph in the bottom here, you can see that there's a much larger value of the acceleration. And it actually peaks at about 9.6 meters per second. So it's actually going to peak pretty close to our actual value of gravity, 9.8. There's a reason why it's not exactly 9.8 though, which we'll end up talking about in a later topic. So that's what we kind of see here. We see that if we pull harder with more force, we're going to accelerate more. We see that if we have more mass that we're trying to pull with a force, that acceleration is going to go down. So we know that force will equal a mass and an acceleration. We know that mass and acceleration have to be inversely proportional. When the mass increases, the acceleration goes down. And we know that as we add more forces, the acceleration can increase just like that. And it makes sense. That's what you see in your day-to-day life. And that's what we saw here in our little lab demo. So what we're going to see next is we're going to look at some of Newton's laws, which deal with this idea of forces. And beyond that, we're going to look at some applications and how we can put all these forces together. Okay? So until next time.